It's my great pleasure to invite you to this month's STEMS webinar. So this is a webinar by Amanda Lenzi, who is our speaker today. So she's currently a postdoc at the Argonne National Laboratory in Chicago. She obtained her PhD in statistics from the Technical University of Denmark, I think back in 2017. Before that, she was after that she went to KAUST as a postdoc, and from there she moved to Argonne. Her research interests involve methods for spatiotemporal data, especially with applications in energy and environmental science. She's also interested in computational methods for large data sets, as well as machine learning for spatiotemporal processes. Today she's going to talk about exactly those topics. So the title of her talk is Can Neural Networks be Used for Parameter Estimation? So with that, Amanda, please go ahead. You can go ahead and share your screen.
Can you see my screen?
Yeah, we see it on full screen and we hear you fine. So please go ahead.
Great. Thank you, Mikael, for the nice introduction and also for inviting me to speak at this STEMS webinar. It's a pleasure to be here and to share my work and what I have been doing at Argonne with everybody here. Today, I'm going to talk about a project which is a collaboration with Professor Michael Stein, with Julie Bessak, with Johan Rudi. Quick outline of this talk. So I will start just with the problem of classical parameter estimation in parametrical model and the challenges that comes with it. Then I will present an alternative way of doing that with deep neural networks for estimating those parameters. I will show how we do that with the methodology. Then I will motivate the problem with a simulated example on spatial extremes with a likelihood that is intractable and very hard to estimate otherwise. Then I will show the methods for an application on minimum temperature in the Midwestern United States, and then I will just conclude after that. So statistical models, usually they are built with the goal of understanding a process. So they're built in from assumptions about some mechanism, and this means that the parameters are often, they have some interpretation, but especially when we are dealing with models for dependence, for example, spatial dependence, those parameters can be hard to estimate from data based on those models. And on the other hand, deep learning is not necessarily built for explaining or understanding a process, but is built instead with having in mind computational performance and generalization. And this means that often there are thousands or even millions of parameters in the model in the more extreme cases, and those have no direct interpretation. So they are designed to fit the data, but they are not very interpretable. So the idea here is to combine the advantages of these both approaches, statistical models and deep learning, in order to model data that have complex interactions and dependencies. So usually in inference, the idea is to use observed data to infer some underlying characteristics of some stochastic process by estimating parameters of some assumed probability model. And that's done by recovering this unknown parameters theta, giving some data that is usually sampled, and they are assumed to be independent copies from this probability distribution that we call here P of theta. So once data is collected, then we call this function as a function of this collected data, our likelihood. And to estimate those parameters, thetas here, we find the values of theta that maximizes this likelihood given the data that we have. So the idea is to evaluate P at the observed samples Y, and this is what is called the likelihood. But often there is no closed form for this maximization problem, and some numerical algorithms or some optimization methods are necessary. But for some more extreme cases, there is not even those optimization or those numerical methods won't work when when you have a larger number of observations. So especially when you have these non-Gaussian models for dependencies, computing this full likelihood, it can be infeasible. But one thing that we note in this case is that it can be feasible to simulate data from this probability distribution, even though evaluating the full likelihood is not possible. So what we propose here is to tackle this problem using a neural network in order to learn these complex dependencies between input and output via the neural network. So what we would like is to find some useful approximation that explains this relationship between theta and y through the neural network. And the idea is, if it's possible to simulate from a model, then we can also perform inference. So to do that, we are going to train a neural network to estimate parameters from simulated data. So the outputs of the neural network are going to be a range of parameter values, and the input of the neural networks are simulated data from this assumed model that we want to estimate from this likelihood using the range of parameter values in the output. So we use simulated data as input, and the parameters used to simulate those data as the output of our neural network. And then we train the neural network using those, and the neural network are going to learn some weights, and after it has been trained, we can give the neural network some new data, our empirical data, and it will estimate what are the parameters of those data. And this works. So the desired outcome here is that we can perform efficient inference by doing this way, in a way that we avoid learning these likelihood functions completely, and instead we learn the mapping between data and parameters directly. So we avoid the problem of evaluating full likelihood that are complicated, but using neural network to learn this mapping instead. So just how we can formulate the problem of parameter estimation with a deep neural network. So we would like to find this function f here for predicting theta, giving value inputs y. So f is a function that maps y to theta, so data to parameters, and our theta hat here, our estimated parameters, is going to be given by something that minimizes some kind of distance between the parameters and this function, which is a function of some weights and a function of the data. So this f is usually going to be the neural network, and these weights are usually composed of both weights and bias of the neural network. And estimating those weights are usually done by training the neural network. And again, this f here is analogous to the argmax, that operation that we have for maximizing the likelihood before, but instead it's going to approximate the relation between y and theta by means of the neural network. And then the next step is to define some kind of criterion for choosing this f. And a common criterion to choose f when you have a regression problem in the neural network is to use the mean square error here as a function of the weight. So the neural network finds these weights. The idea is that the neural network is going to find these weights such that the fit gets as close to the observed points as possible, where proximity here is defined by the mean square error. And the neural network does this, solves this problem usually using some batch gradient descent methods inside the neural networks. And there are packages and ways of doing that. Next, we have to decide which neural network we are going to use. And here, because we are dealing with models for dependencies and mostly spatial dependence, we choose to use the CNN, which is commonly used for finding complicated features in 2D images, which is similar to our data here, which is also going to be 2D. So the CNN usually alternates between convolutional layers and this subsampling or pooling layers. So in the convolutional layers, there is a multiplication between parts of the images and some set of weights, which are trained within the CNN. And you apply these weights to different parts of the images. And by doing that, the neural network can find some features anywhere in the image. So this weighted average of the inputs is what composes this convolution, and these filters are activated when some features of the data are detected. And then the subsampling is something to summarize these features afterwards, which is usually the maximum of a block after you apply the weights, and then you go back and do some convolutional layer and some more subsampling. And then finally, the last part is this fully connected layer that flattens the image into a column vector, and it learns these nonlinear combinations of these high level features. So this is the type of neural network that we are going to show in our examples, because we are dealing with data with spatial dependence. And the CNN seems to be working well for that. Now I will move to some motivation example for using CNN to estimate parameters of likelihoods that are quite complicated. So if you think about spatial extreme and like stable processes, the likelihood is intractable even for dimensions that are not too large. So here is an example of some simulated max stable process with different parameter values for different range and smoothness. I'm going to talk more about max stable process in the next slides. So this max stable process, they are used for studying extreme events that are recorded in space and in time. So they are the multivariate version of the GEV for modeling extremes. And these processes are well known for having these likelihoods that are intractable. And our aim with this example is to demonstrate how we can use our method and neural networks to recover parameters of a model with intractable likelihood by learning the map between parameter and data. So this is just some definitions of max stable process before I show the numerical simulations and examples that we did here. So if we assume that you can find these sequences of A and B here, so consider that we have observations Y1, Y2 at some spatial locations of a process. Then the max stable process is the limit process of this normalized pointwise block maximum process. So if you can find sequences A and B such that this limit exists here, and this limit has a distribution with no non-generative margins, then this limit has to be max stable. And the second definition here of this process Z of S is the one that is more useful in practice. So to define Z here, it's taken the maximum between these two processes here, these two components. The first one is the points of a Poisson process from 0 to infinity, and these W's here, they are independent copies of some non-negative stochastic process with the mean equal to 1. So the Poisson process is fixed, but this W here, you can choose depending on the application in order to fit the data that we want to model. And several choices of this W here is going to change the type of max stable process that's being estimated. And this max stable process has this Uni-Frechet distribution here, giving with this CDF exponential of -1 divided by Z. So it follows from the second definition that you take the maximum of the Poisson process and the W, that the CDF of Z can be written as the, so this probability that all the Z's are smaller than some Z1, ZD, where D is the dimension. And this, you have this exponential of -V, where -V is the expected value of the maximum of all these W's divided by this Z here. And to get the PDF from the CDF here, we have to take the derivative of this function with respect to all these different Z's. And when we do that, we have again this exponential here, but then we end up with this sum of these multiplications of V of pi L, where P denotes the collections of all the possible partitions. So this derivative here with respect to V, you have to take all the combinations with all the Z's in this likelihood. And because you have this sum taking over all these partitions, you end up with an explosion of terms. And even for dimensions equal to 12, you already have too many terms, and evaluating the full likelihood, it's basically impossible. So there are several ways of approximating this likelihood, since you cannot write it the full likelihood. And one of the most common way in the literature to write down the likelihood is to just select pairs of observations instead of taking them all. So we write the likelihood just by using pairs. And when you have just two, then the likelihood is simple. It has only these terms here, and it can be written explicitly. Then these alphas here, they are weights that can be included to weigh the different pairs. So usually what is done is that after a certain spatial distance, this alpha is equal to 0. So the pairs are excluded from the likelihood, and for some threshold and a smaller distance, then these weights are usually set to 1. But the problem of using this approach is that there is no obvious way of choosing which pairs to include in the likelihood. And there is still a loss in efficiency when making inference for high dimensional data. So this is still a challenge. So our contribution to this problem will be to, instead of using this approximate likelihood method, to use a neural network to estimate the parameters of this intractable max stable likelihood in dimensions that are a lot larger than the 12 or the ones that you can do with the full likelihood. And also we are going to show how we can quantify the uncertainty of those estimates as well. Oops. So we choose one particular model for the max stable, for the W part of the max stable process, in which we choose the one that is called the Brown Resnick. So the Brown Resnick is a very popular choice for modeling the spatial extremes, because it's able to generalize several other stationary max stable process. And it's defined using this epsilon of I here, which are stationary Gaussian process with a semi-variogram that it's defined like this. So it depends on two parameters here, some range lambda and some smoothness nu, and it's a function of the Euclidean distance between the pairs of locations. And how are we going to estimate parameters of this model using our CNN estimator? So the first part is to simulate training data for the CNN. So we simulate data here that we call Y-train from this Brown Resnick process. And to simulate this data, we first need to define a range of values for the two parameters, the lambda and the nu. And in this case, because the test data is simulated data and we know what those parameters are, we just simulate lambda train and nu train by uniform where these A and these B's here are functions of the parameters actually used to simulate our test data. So we first generate those 2000 values from uniforms of these two parameters, and after we have those 2000 pairs of lambda and nu, we simulate data from a Brown Resnick process, as it's explained here. After that, we train the CNN using those simulated data. So here, instead of modeling the data directly, we use a log of the data as the input for the CNN, and for the output, instead of using the parameters, we use this variance stabilizing transformation where we take the log of the range, and for the nu, we divide it by this 2 minus nu, just to make sure that the smoothness is between 0 and 2, or is smaller than 2, as it should be. So after the CNN has been trained with this data and parameters that are simulated, then we can estimate the parameters in some test data or in some real data by giving images to the training CNN and obtaining the parameter back. So this is how we are going to estimate using the CNN. So here are some first results from this simulated example here. So we simulate with lambda and nu varying between here to 0 to 1.8, and the lambda goes from 0 to 2.5. So the cross here represents the true value in this test data here. So these are not data that are used to train the CNN, but these are the ones we want to predict. And then we compare the performance of the pairwise likelihood in red, and the CNN is shown in green. So small to large ranges are shown from left to right in these plots, and rough to smooth are from top to bottom. And each dot in each plot represents a different test data, which are simulated with the same parameters, and they are simulated independently and also estimated independently with the two methods. So we see that there is larger variability in the estimation for the pairwise likelihood, especially here when you have larger values of the range lambda. The parameter seems to vary quite a lot depending on the test data set that we are estimating. And the CNN seems to have less variable estimates for most or for all the test data here, the different parameter values that we use to test, and it has less variance and also a less bias, it seems. And here to find the estimates from the pairwise likelihood, we try to help the pairwise as much as we can. So we started with 20 random values around the truth, and then we do the maximization with all of them. We take the 5 that has the larger likelihood value, and then for these 5 we do the full likelihood with or the pairwise for these 5, and we take the one that has the largest likelihood out of these 5, and those are the ones that we use as the initial estimates for the pairwise likelihood. But still we get some cases where it's off, especially when you have here these low values of lambda, as we see in the last row. So next, I will show now an application of our method to some temperature data in the Midwest US. So this is an example of temperature minima from a 10-day block in May 2000. So what we have here is data in a grid spacing of 12 kilometers in the Midwestern US. This is hourly data between 91 and 2019. Here we are focused on minimum temperature data from these 10-day blocks, and we select only the spring months, so April to May. And that's to minimize the effect of seasonality in the model. And we also perform some spatial downsampling. So what is shown here in this figure is some downsampling where we obtain images of size 25 by 25, which is the same size as the simulated ones that I showed before, so that it's easier to compare. Here it's shown the steps needed to estimate the parameters of the model with this temperature data, minimum temperature data. So this is a bit different from the simulated example I showed before. It has some extra steps because the simulated example assumed that the data comes from a unit Fréchet distribution, but real data rarely does. So first, what we need to do is that we need to fit these local GEVs to each location independently. And then after that, we get the parameters of the GEV, which can be used to transform the data to the unit Fréchet. And after its unit Fréchet, then we can fit our max stable model, which here is the Brown Resnick again, using the two methods, the Pairwise and the CNN. And in this case, we first fit using the Pairwise likelihood, and we use these estimates from the Pairwise likelihood as some crude estimates to how we are going to generate data and parameters to train the CNN. So those are, we increased the range a bit from the ones that we get from the Pairwise. We generate parameters and data, then we train the CNN, and after that we can compare the predictions in the real data from the CNN with the Pairwise likelihood. So this is what we call the data pre-processing. So before we can go to the max stable fitting, we first fit a GEV to each location independently. So recall that we have these 6 periods. Each of them is 10-day minima. And we take the period from April to May. So we assume that Z at some period P, where we have 6 periods because we have these 3 months of data. And at year I is going to be a GEV that has a location parameter here that depends on period. Since even though we are only considering spring, there's still quite a bit of variability in spring in the Midwestern. So we assume that the location parameter still depends on the time or on the period. And then we assume that the scale and the shape parameters are the same for all the time. And we fit this GEV here for each of these 25 square locations in our gridded example. So here are example of the estimated parameters for each of these pixels. Recall that we are modeling minima. So what we are modeling is the negative of the temperature. So that's why you see higher values in Canada and also for the periods where it's actually colder. And as expected, the period 6 here, it's quite different from the period 1. And it changes smoothly from period to period. So it shows that there is still significant difference in the temperature from period, even though we are only considering spring. And the shape and the scale parameters are shown here in the last row. And the shape parameters are primarily negative, indicating a bounded upper tail in the distribution. And that's usually what is commonly observed for temperature data. So next, after we have fit this GEV for each location independent, we can transform the data to the Fréchet scale and estimate the parameters again of the Brown Resnick process using the two methods. Again, we are going to use the pairwise likelihood, and we have these 174 transformed data images that we are going to predict or to estimate independently using the pairwise likelihood. So it's 174 because we have 29 years and 6 periods. And we just fit the pairwise again using the spatial extremes air package in a similar way that we did with the simulated data. For the CNN, we need the training data. And again, to generate the training data for the CNN, we use the estimated parameters from the pairwise as some idea for the initial values. So we perturb the values from the pairwise, and we generate 2,000 different ranges and smoothness. And based on those, then we simulated data from the Brown Resnick process. And those data are input to the CNN as training data, and then we train the CNN, we get the estimation of the CNN, and then we can give this 174 passing images and get what the parameters for those should be. So here is an example where this is done. So in each of the one plot is for one parameter, which is the range, and the one on the right is for the smoothness. So on the x-axis here for the two plots are the estimations from the CNN, and on the y-axis are the estimations for the pairwise likelihood. The color of the dots represent the 6 periods from April to May. And the CNN estimate larger ranges for most periods, we can see. So the values of the CNN here are larger than for the pairwise. And on the other hand, here for the smoothness on the right, we see that the CNN values are concentrated around 1 and less variable than the pairwise, except maybe for period 1 and 2, where the CNN estimate quite large values of this smooth parameters. So next, to evaluate the performance of the two methods, we look here at what's called the F-matogram and the connection of that with the extremal coefficient. So this F-matogram is a summary statistics for this extremal coefficient. And the extremal coefficient, it gives a measure of the extremal dependence between two stationary max stable random fields. And it's given by this expected half times this expected value of F, which is the Frechet margins of this max stable process Z's here. And for the extremal coefficient, it goes from 1 to 2, where 1 corresponds to perfect dependence and 2 corresponds to independence. So here we show the results of those extremal coefficients and F-matograms for the two methods. So the black dots in the left plot are the empirical values. So each of these dots correspond of these F-matograms between pairs of locations, considering all these 2000 by 2000 locations and 174 replications or temporal images. And the green here is the CNN, which is a bin version of the estimates with 100 bins, and it's the same for the pairwise, which is shown in red here on the same plot on the left. And we see that the pairwise is estimate values that are usually higher than the empirical ones. So it looks like it's underestimating the extremal dependence, especially at a larger distance here. Even though larger distances, it's more variable and it's harder to estimate, and also there are less pairs in that case. And on the right, we can see what is the spread of the two methods. So we take one of this 174, we select one pair of estimated range and smoothness, and we simulated 200 data sets from Brown Resnick using those estimated parameters. And this is just the 95 interval of those simulations for the two methods. And again, the pairwise likelihood has a larger values or larger values of this extremal dependence, meaning that it's showing that it estimates that the pair of locations have not as large spatial dependence, and the pairwise likelihood has lower values of the extremal coefficient, which matches better the empirical ones shown on the left here with the black dot. So it looks like the CNN is doing a pretty good job at capturing the pairs that have a high extremal dependence, especially at larger separation distances. Another way of visualizing how the two methods compare for estimating quantiles here. So the first plot is for minima, and then second is for mean, and the last one is for the maxima. And those are 95 confidence intervals based on these 200 simulated replicates for each of the 174 data sets and for all the 25 by 25 sites in our data set. And we see that the CNN outperforms the pairwise here, especially for the lower quantiles and for predicting minima and for predicting mean from the two first plots. The CNN is closer to the diagonal, meaning that the model is matching the observed quantiles better. And then when you look at maxima, the CNN, especially for the lower values, lower quantiles here, the CNN is below the diagonal, and the CNN, sorry, is on top of the diagonal, and the pairwise likelihood is on the bottom. So it looks like the spatial dependence in the extreme for maxima, and for these lower quantiles is underestimated by the pairwise likelihood and actually underestimated by the CNN. Yes. So next, how can we look at the uncertainty of these estimates from the CNN? So far we have only looked at the point estimates, but how can we access the uncertainty? To do that, we use a modified version of parametric bootstrap. So whereas in the classical bootstrap, we need to be able to fit and to simulate from a model, here we only need to simulate from the model because the CNN does the fit, so we don't need to be able to fit max table process to perform parametric bootstrap. And as usual, what we do, we train the CNN. We estimate the parameters in our 174 data sets independently for each period and for each year. Then we create for each of these estimates bootstrap data sets by sampling 500 times from Brown Resnick process using the same CNN fit. So we just feed the CNN once. And then after that, we again predict we estimate parameters in these bootstrapped samples, all these data sets, and from those we can compute confidence intervals or whatever statistic we would like. So here is showing for the first period only. So we do this separately for each year and for each period. So in the x-axis here, we have our 29 years. This is only shown for the first period because the others were similar. And each of these bars corresponds to the CNN estimates from these 500 bootstrapped samples using the CNN for that specific year, doing that specific period from the original data set. And you see that the left is for the range, the right is for the smoothness. And we see that the width of the intervals vary from year to year. And it seems like it's reasonable to have those intervals for the CNN. So what we do next is to have a look at the calibration of our predictions from the CNN, how we compare calibration here. So again, we use bootstrapped samples. So we train the CNN and we predict those 174 data sets independently. Then for each of these 174 estimates, we create these 500 bootstrap samples. We estimate those parameters in these 500 samples using the same fit of the CNN. And then from those 500 samples, we can construct confidence intervals. Here we construct from 5 to 95% empirical coverage. And then we do that over the 29 years and for each of the 10 periods separately. After we have computed all these different intervals, depending on year and on period, we count the number of times that the value most often covered by these 29 intervals during a specific 10-day period is contained in the bootstrap interval. So here we consider that the years are independent replicates of the periods to get the empirical coverage. So for example, if we have 90% our 90% confidence in bootstrap confidence interval, it should include the most covered value here that we choose roughly 90% of the time. So more or less 26 years should be smaller or equal to the 90% quantile of these bootstrap samples. And that's how we compare coverage, nominal coverage and empirical coverage. So this is what those plots are showing. So each of these lines is for a different period. We show the coverages for each period separately. Again, we showed separately for range and for the smoothness. So the x-axis here is the nominal coverage and the y is the empirical coverage. If those match exactly, then we would expect the perfect reliability and the lines would be in the diagonal of the plot. So looking at the different quantiles for these predicted parameters that are calculated from these 500 bootstrap samples, we see that especially for the first periods, it's quite well calibrated with the points close to the diagonal, and then there is some overestimation for some of the periods here, especially for larger quantiles, but that's to be expected when we use the value that appears the most as the true value, and that might be a result of that. And for the smoothness, we see a similar pattern. So again, the period 1 and 2 have points that are closer to the diagonal, and then the periods where we have a larger temperature, the last periods, there is some over coverage that we can see from these plots. So just to summarize what we have done so far, so we have shown a way of using deep neural networks to estimate parameters of likelihoods that are intractable. So our method has some similarities with approximate Bayesian computation, ABC. But one advantage is that it does not require choosing some summary statistic metric that has to compare simulated data from the posterior with empirical data, because that is done inside the DNN automatically, this mapping between data and parameters, so we don't need a metric to compare them. Also, with the DNN, we just train the neural network once, and we are able to predict as many testing data as we would like, and that is very fast after the neural network has been trained. While with the ABC, you need to redo the procedure every time you get a different data set. Also, by using neural networks, we can take advantage of this of recent algorithms for CNNs and for DNNs. So there are a lot of recent advances of ways for the neural network to learn features from these high complex images while being fast and easy to apply. There is still the concern that these are black box, and it's hard to understand what it is doing, and also it's somewhat restrictive and artificial. We also assuming this procedure that we don't know anything about the likelihood or about the mechanism that is generating the data, which is not true. some extensions of what we did and some things we are looking at right now. So it would be very interesting if we could understand what these neural networks are doing and how it is finding this mapping between data and parameters. And we think that it might be related to the sufficient statistics. So similar to what maximum likelihood would do, maybe it's finding the sufficient statistics of the data. Also, this idea could be applied to other statistical models that have likelihoods that are difficult to estimate. For example, some non-homogeneous Poisson process or some epidemiology models that we would like to test our method. And more recently, I'm looking into developing some methods to improve the training data for the neural network. So far in what I've been shown before, we either had simulated data where we knew what the real parameter values were, or when we had data, we could use some perturb the estimates from an approximate method. In this case, it was the pairwise likelihood in order to generate parameters to train the CNN. But it could be that if we use parameters that are far out from the ones that from the test data, the neural network just won't find and won't give good predictions. So how can we know that we are generating training data that are in high density of the parameters of the testing data? And one way is to use one way that could work for time series data, at least, is to use a very large unified database where you can generate time series, a very long time series, and that will help the neural network to be more stable on the training. And then you can predict time series of different lengths by just replicating the time series if you assume that they are stationary. Also, I'm looking to building some iterative training procedure that guides the simulations to the parameter region of interest, so that future simulations are more informative about the parameters that we want to infer, and that at each iteration, the DNN becomes a more accurate model of the likelihood in the region of high density for these parameters. With that, I conclude what I wanted to show you in this talk, and I'm happy to answer any questions. Thank you very much for coming and for listening to my talk.